Hello everyone. I hope my screen and voice is clear. Okay, so let's get started with today's session. Let me just share my presentation. Yes. So today, we'll be continuing what we left in the yesterday's class. We'll be focusing towards some more ML algorithms, which would be very useful for any data provided. Yesterday we did saw the importance of support vector machines, right? So how did it can able to create a better a proposal or a better tangent that can able to classify or that can able to divide two groups of data. And we did also saw some different other techniques like bagging, boosting, basically all the ensembling techniques. And we kind of ended up with random forest. And we did know that using the same data set PIMA Indian diabetes, we were able to get a maximum accuracy of 77%, right? So, and that 77 was achieved using random forest. And we didn't even tune any hyperparameters in that. So basically I would say yeah, so each and every algorithm has its own pros and cons, because you will be wondering that if random forest succeeds really good, why can't I go with that particular algorithm every time I want? But it's not like that, because it's totally depends on the data intensity. Because if the data is kind of imbalanced, okay, if there is a missing gap, then definitely ensembling technique will definitely do a good job, because of the fact it has multiple models that works together to solve this particular mystery. Obviously random forest will do a good job, or maybe any boosting techniques like add a boost or gradient boost or something like that. But apart from that, when you have a perfectly balanced data but you have more number of features to deal with, in that particular situation, definitely your random forest will not be doing a good job. So today we'll be focusing on a few more algorithm which I told you before. The first and the simplest algorithm, which I would say, is the k nearest neighbor. Okay, k nearest neighbor is one of the simplest algorithm, I would say, and it is proven to be more effective for a data which is kind of doesn't have a linear pattern. Because usually that whenever you have a linear pattern altogether, obviously you naturally go with support vector machines or decision trees or something like that. But in this case, even though the data is not very linear in nature, don't mind, because all I'm going to do here is I'm going to look for the neighboring pixels. So the algorithm works as in the name implies. You can very well see here, it is nearest neighbor, which means that whenever I have a query data with me, okay, whenever I have a query data with me, okay, so I will be using this query data and see the nearest neighbors. Okay, I'll be seeing the nearest neighbors and kind of formulate what this data or where this data might belong to. Okay, so that's how this k nearest neighbor work. I'll just give you a good example for it. You can see in this particular chart, right? So where I have some data which is in class A, that is in yellow color, and some data which is in class B, and that is in purple color. Okay, and now let's consider this star to be my query data. Okay, so this star is going to be my query data. Okay, so using this query data, I'm going to see this data, which class it belongs to. Now what I do is I'm going to keep this k to be 3, which means that I'm going to look only 3 neighbors which is close by to this particular data, which means that I'm going to look for, I'm going to calculate the distance with all the data, okay, with all the data which I have, and I will be seeing which top 3 are the closest one to this particular query data. And it is evident that these 3 data are very close by to each other. I mean, okay, so this 3 data is very closer to this query data, which means that I'm going to consider these 3 data for my for my inferencing or for my classification purpose. So it is evident here that you can see here we have 2 class B data, correct? We have 2 class B data and 1 class A data. So which means that this query data might belong to class B. Okay, so I'm going to infer it, or I'm going to classify it using this particular technique. So I'm going to have a query data. I'm going to place that query data wherever it is situated in your particular data distribution. with that particular point as a center, I'm going to look for neighbors. In this case, I have 3 neighbors, and I'm going to look for 3 neighbors. You can choose your own neighborhood. Okay, so you can either go with 3, 5, 7, 9, 11. You can go all the way along to any numbers, and as long as it is an odd number. Okay, because the golden rule for k nearest neighbor is you have to use an odd number for the same, because without odd number there will be inconclusive results. Because sometimes if you go with even number, let's say 8, in that case maybe sometimes you might be having 4 for class A and 4 for class B. So this will put into a dilemmatic situation. So that's why we usually go with an odd number. And using this particular technique, you can play with an hyperparameter known as k. Now let's take k is equal to maybe 6. Okay, I'm just giving an example here. Okay, it's, usually, as I told you, like we usually go with an odd number, but nevertheless, in this case, I'm just going with k is equal to 6, which means I'm going to look for 6 closest neighbors. Okay, so here I already have 3, right, and I am looking for 3 more neighbors which is close by, and you can see this one, this one, and this one. These 3 are the closest neighbors. So which means that when I calculate the distance from this point to all the data, I can able to sort this out from the ascending order. So where I'll get the top 6 queries, or any number of queries which is required. And with this 6 neighbors, now you can see that only 2 data belongs to class B, correct? Only 2 data belongs to class B, whereas 4 data belongs to class A. So now this entire classification is totally different, because now this query data, I will be classifying it as class A because of the fact I'm using some 6 to 7 neighbors, and it is evident that my my data or my query data is going to change accordingly. So is it really a useful algorithm? Now this will come into mind, because you will be wondering that, okay, I can simply go and strike a line like this. That would be like create, that is more than enough for me to utilize, which is similar to your support vector machine. You always go intuitively and maybe use support vector machine, or maybe even you can use decision trees or boosting or any different techniques. But why this k nearest neighbor? As I told you, I'll give an example here. Okay, so let's take few more classes like this. Okay, so I have some classes here and there, and I have a clustered data somewhere like this, and some more classes like this. So imagine when I have a data like this, okay, and my query data is going to be this one. Okay, so imagine when I'm having a highly variated data like this. Okay, so when the variance is too high, okay, obviously it will be very tough for my model to converge. Basically speaking, your support vector machines, or decision tree with different branches, obviously it's going to be tough because it's closely packed and all the datas are being kind of mixed up together. But one point to be proven here is like it is kind of forming a locality, correct? I can see a locality here and there. Some clusters are being formed here and there, but here, yeah, I mean, I don't feel like there's a cluster, but yeah, somehow a locality, oh sorry, the locality would have been formed. Okay, so when I do in that situation, for example, if I have a clustered data like this, and I have a query data which is here, obviously when I look for neighbors, obviously the closest one would be like this one, and this one. Or if I go with 5 neighbors, I'll be taking this one and this one. If I go with 7 neighbors, if I go take this one and probably this one. So when I consider only these guys alone, okay, so let me take these guys alone, which is probably your 1, 2, 3, 4, 5, 6, 7 neighbors. So out of these 7 neighbors, okay, it is very evident that I have a lot of blue dots. So I can certainly say it as class blue. Or if I have more yellow dots, that belongs to class A, I can readily go with class A. So which means that when you have a clustered data, okay, when you have a clustered amount of data, then it is better. It is always better to go with k nearest neighbor, because k nearest neighbor is very, very simple in nature. Because all you have to do is you're gonna do a search index and try to distribute all the data and find the distance between all these numbers. So right after the query data comes into play, you kind of take the search index and match with your actual query data and find the distance between all your all the data which is distributed. With that, you will be getting the distances. With that distances, you can find the top or the least 5 or the least 3 or the least 11 neighbors. Based on that, you can make a unified decision. Okay, this is how a k nearest neighbor works. Okay, is there any doubts or clarification at this point? Okay, I suppose there is no doubt. So I'll just quickly walk you uh, through the code for this k nearest neighbor. Okay, so yesterday we did utilize this data set named PIMA Indian Diabetes, correct? So I'm going to use the same PIMA Indian Diabetes data set. I'm not going to do any modification to the code where I load the data, pre-process the data, split the data into input and output, and furthermore split the data into training and testing. Like all these things will remain the same. The only change which I've done here is this particular fourth line where I have added sklearn.neighbors import k nearest neighbor. So only this particular function have been loaded. Okay, so with that, you can see that I'm just going with the same content, the same code. Only line which I've changed here is this 24th line where I've called this function k neighbors classifier, and the only important keyword or the only important parameter which you want to give here is the n number of neighbors. So that's going to be your k. Okay, so what is your number of neighbors? So only I have to give that number. In this case, I'm going to go with 5. Okay, I have the model. I'm going to train my model. Let's see like how it performs for the training data, for the testing data, and also let me create a confusion matrix to see like how better it performs. And we know the previous benchmark for this particular data is your you know uh, was 77 percentage, right? So it was giving us to the maximum 77 percentage. Let's see if we can beat that particular value with this k nearest neighbor. So for that, I'm gonna go open my command prompt, activate my model, and I'm gonna run k nearest neighbor. Okay, so let's take this guy little aside, and you can see uh, the value which I've got here is 66 percentage, which is not really good, I would say, right? Because obviously like we were getting a decent 70 plus accuracy for any decision tree or any model we had. So I don't think so this model is doing a good job. So maybe let's try to, and again, like you can see there are a lot of false positives here. So let me try to change the neighbor. Okay, so I'll just change this neighbor to 11. Okay, let's see like how it performs now. Okay, this is improving now because from 66 it has improved to 69. That is a good a good relief, I would say. Now what if I increase it furthermore? Yeah, that is even better. I've reached 74 percentage, which is again a really good number, I would say, right? Because I've reached a decent amount of accuracy, and you can see like I've got a good number of you know uh, 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 true positives and very less false negatives and false positives. That's a good sign. Okay, so maybe let me, since it is like increasing exponentially based on the number of neighbors increases, I'll make it as 15. Let's see like how it performs. Now, I guess it is almost the same as we saw, but only good thing is like, the recall for class zero is even more increased. That is a good sign. But the recall for class one is kind of little bit decreased, which is very evident here because you can see we have only 19 numbers which has been falsely detected. Okay. So now again, maybe let me go and fine tune it even more to 17 neighbors. Okay, now you can see there is a decline rate, correct? So as long as I had it for, to a maximum neighbor count of, what is that, like 15 or 13, it was giving me a decent result, right? But right now it is not doing a good job because obviously the data is getting like, deteriorated. And mainly it is because of this class one, because there's maybe the distribution of this particular class one data is not really doing a good job here. Because of that, you can very well see like the values are being decreased. You can see from this point, from 65 59, it has been it has reduced slightly from 59 to 55, and here it is 46, which is a bad sign. And but you can see like the precision recall of this uh, class 0, it is kind of the same. It's almost the same, just like having a mild fluctuation, but this recall is going very bad here. So that is a sign where I might maybe like I can stop and go to the neighbor maybe 15 or 13. But what if I use 101? Just out of curiosity, I'm going to use neighbors 101. Let's see like how the model performs. Surprisingly, you can see here, right? So it is giving me 73% of accuracy, but it doesn't matter, because the more data you take for a custom, or for for a cloudy data, or how do I put it, like for an intense data which is close by packed, if you go with more number of neighbors, you might be ending up with even with a wrong classification. Let's say if I go with maybe like okay, I'll go with 301. Let's see like what happens now. Okay, so now you can very well see here, this is completely lost. The class 1 is completely lost, like you're literally getting it as 0. Okay, so that is a problem, correct? So obviously I might not be like using this, because obviously the entire data set is only like having 700 data, right? So if I go with 300 or something like that, then definitely it is going to fail. Yes, I will share the code like once after the class is done. But yes, I would say like from yesterday's code, you can very well change this fourth line, where I'm going to just add this k neighbors classifier, and I'm going to change this line alone. Only this 2-line change from the previous code which I've shared yesterday. You can use that to train any model. So that's what I'm saying. So you can very well go to scikit-learn documentation. Let's say if you want to go with let's say okay, so I'll just go with this k nearest neighbor scikit-learn. Okay, I'm going to knn and scikit-learn. I'm going to go to this first link that it opened, and you can see the function is here, correct? So scikit-learn.neighbors.k-neighbors classifier. So I just imported that function, scikit-learn.neighbors import k-neighbors classifier. Either I can use like I'm just importing from a function, or I can just call it entirely. Instead of using this k-neighbor classifier, I can directly import scikit-learn alone, and I can call the entire name here, okay, which is like scikit-learn.neighbors or k-neighbors classifier. Okay, and you very well get all the documentation which is provided for what are the other parameters which you can use for this particular model, where you have n neighbors, weights, algorithm. This algorithm is something like a searching technique, auto search technique, and there are many other different methodologies to be taken care of. And sometimes the metric will be like Minkowski, which is something like a weightage mechanism. I'll just teach you that sometimes. Okay, so I'll just go with another parameter here. Okay, we know that like neighbor 13 was giving me good results. I'm gonna go with another parameter known as weights, is equal to distance. Okay, so as a default, uniform will be used, which is something like value of both precision b1. Yes, absolutely. Recoil and precision can become one if all the detections are predicted correctly. Okay, if there is no false positive and there is no false negatives, then definitely it'll turn to one. I'll come to that point a little later. I'll just finish this, this particular parameter known as weights. So let's take an example here. Okay, so in this case, we know that like we kind of calculate the neighboring pixels based on the query data. But if I use this weight is equal to distance, okay, for example, if I have purple data, which is very, oh, sorry, maybe I'll just go with yellow. I guess I don't have an yellow function here. Yeah. So let's take one more data, which is here. Okay. And there is a purple data, which is here somewhere. Okay. So now if I go with, oh, come on. Really sorry for that. I'm just going to keep a purple data here and an yellow data, which is very close by. So as I told you, okay, as I told you that when I use my weight is equal to distance, okay, I'll be looking for 5 neighbors, obviously. Okay, if I give k is equal to 5, okay, I'll be looking for those values. Okay, for example, I'll be looking the distance for this 5 closer guys. But instead of rationally, considering these three as class B and this two as class A, I'll be looking for a way on how closer my data is. For example, you can see this class A is very close to this query data, even though I have three class B's, and for class A I have two data, and for class B I have three data, which is clearly indicates that class B is the winner because I have more data in class B. But when I keep this weight to be distance, what happens is like whenever a data is very, very close to my query data, if it is very close to my query data, then obviously that will be given more weightage, which means that this can be, sometimes I can even say the output can be class A as well. If both the yellow points are very close by and all these three purple points are very away, based on the closest distance, I'll be giving more weightage to those data alone. So yes, you'll be wondering that will that be useful? Yes, creating a bias can help at some point of time, but not every time. Okay, only for particular situations, this might help out really good. Okay, so I'm going to change the parameter weight is equal to distance. Let's see like how it evolves. Let me run it. Okay, it's 72, which is not bad, but for the same settings, okay, I'll just comment that weights function alone. For the same setting, I was getting like 74%, right? Which means that having a distant parameter is not really helping me here, because you can very well see all the values have been reduced drastically because of this weightage. So, which means that, maybe what I can do is on a quick note, I can, reduce the number of neighbors and try to run it. Okay, to see like the impact of the distance parameter, but you can see like the performance is again degrading, which is very evident that for this particular case the model is not doing a good job. You can see very well here the model overfitted, okay, because of number of data which is very, very close by. The model is kind of overfitted against each other, but you can see like here, right, it's not overfitted. The training I guess is like only 78%, whereas the testing is 74. And similarly here it is overfitted, and which is not a good sign, where I've given like 300 as my neighbor, right? So that's why it is being overfitted. Likewise, I can see always not only look for the test data alone, and also you have to see the training data also. Training data should not be overfitted too much. If it is overfitting too much, then it can also raise a problem. So this clearly states that when I keep weights as uniform, when I give equal weightage to all the data, it certainly gives me a good result. I'm just saying it again very loud, that this is not mandatory, or this is not the standard practice for any data given. But yes, the default parameters usually works better. But for some cases, okay, that's not the end of the end of the world. You can always try and tune these parameters and see like how it evolves. You should not be saying that, okay, I've got like this much of accuracy, okay, maybe I cannot evolve from this point of time, I have to go look for more data, or a different architecture. So let's not do that. But before we take that switch a conclusion, always it is better to go with all these kind of different hyperparameter tunes to see like which is fitting my model in a better way. Okay, so I hope this is clear, right? Is there any doubts or clarification at this point? Okay, since like they have asked about precision recall, I'll just give you a very a simple idea about this precision and recall. So okay, perfect. So I'll just type the formula for precision and recall. Precision, okay, is equal to true positive plus false positive divided by true positive. Okay, and recall is going to be true positive plus false negative divided by true positive. Okay, now you can very well see here that, okay, for example, true positive is like, the correct predictions. For example, if I have 100 data with me, in that my model has predicted 80 images correctly. It has classified 80 data correctly, which means that I have a true positive of 80. And out of that, I have some false positive, which means that instead of class A, it is saying it as class B. Okay, it has to predict it as class A, but instead it is saying it as class B, which means that I have 10 data that is false positive. Okay, and I have 10 more data which has been left behind, which says that there is no classification, or which is having very less confidence, which means that this 10 data can be treated as false negative, which means that there is no classification done at all. It's saying that this image doesn't belong to any classes because I have a very, very less confidence to deal with. So with this numbers, you can very well see here, true positive is very good. I have 80 numbers, 80 data have been detected very correctly, but 10 numbers have been detected as class B, and 10 number of data had not been detected at all by the model. So now when I substitute these values here, what happens? 80 plus 10 divided by 80, correct? So which will ultimately give me a value, uh, uh, let's say maybe a value which is uh, closer to not closer to 1. Let's say it'll not give me the right value, obviously, right? It will not reach towards 1. And similarly, when I use this false negative also, I'll be ending up with having very less number. But just imagine if I don't have any false positive at all. Okay, and if I don't have any false negative, out of this 100 data, all the data I have detected correctly. All the 100 data are true positive. Now what will happen? This will become 0. So 100 by 100 is going to give you 1. So obviously, yes, you can reach precision and recall to 100%, provided if all the data have been detected correctly without any false positives or false negative. Without false positives and false negative, yes, if all the images have been detected correctly, then definitely you'll be, getting the right results. Okay, so this is one important thing which you want to keep in mind. Okay, so this is one thing. Yeah, so this is all about k nearest neighbor, guys. Okay, so I hope this is clear, loud and clear. Yeah, so now let's go for the another important algorithm known as logistic regression, because this logistic regression is very, very useful algorithm, because this algorithm kind of paved way to neural networks, because we know that in the upcoming session we are going to cover more about neural networks, right? So in that particular case, neural network is kind of evolved, it was kind of created because of this logistic regression algorithm, which is very, very similar to what we see in our modern deep learning algorithms, like your normal neural network, convolutional neural network, your chat GPTs, transformer model, large language models. For all these things, this particular loss regression kind of paved the way, because this is where a concept known as loss, a concept known as activation function is kind of formulated here. Okay, I'll just give you a very simple insight about this loss regression, because it's a very big formula to be derived. Let's not derive any formulas here. I'll just teach you how this logistic regression works on a higher level. Okay, so here you can see that I have some data. You can see as the XY axis indicates, you have the X axis that shows a number of hours students are studying and probability of passing the exam. So you can see when the number of hours increases, when the number of hours increases, the probability of student passing is also becoming denser and denser, right? In this region, it is becoming denser and denser. Yes, we might have some students who might be doing a good job, but you can very well say and very well evidently say at this point, at this particular point, you can see like, below 1.5 hour, everyone is failing. Okay. Only above 1.5 hour, people are passing, but there's a very big gaps in between this. There's no support for this data, which means that this is a closely packed data. So which means that people who are studying between 3.5 to 5 hours or above, they have a good likelihood of passing the examination. So this is the data which I have. Okay. So certainly, yes, I can draw a line like this, right? I can draw a line like this and I can able to classify it. As I told you, like, yes, support vector machine will do this thing because, there is no other data which is distributed here. There is no other data at all, which means that this line can be, very vertical in nature. No matter like what kind of, strategy you use, this will end up, creating a straight line. But, this data itself, it looks like yes or no, correct? It looks like an yes or no. More they study, more hours increases, people are passing, less are people are failing. So that's the that's the essence of it. So in this case, I can form a regression strategy where usually what regression do, it tries to follow these numbers, right? It will try to form a line that follow these numbers. That's how regression do. But in this case, I'm going to use the same regression strategy, but I'm going to define whether it is 0 or 1 or yes or no. Okay. In that way, I'm just, classically converting my linear regression into logistic regression. Okay. So logistic regression, as the name implies, it's a kind of a linear regression strategy, but I'm using it only for yes or no, which is something like, I'll be keeping a threshold here. Okay. I'll be keeping a threshold on as maybe 0.5 or something like that. Whatever data which is above 0.5, I'm going to say it as 1. Whenever it is below 0.5, I'm going to say it as 0, something like that. Okay. So, okay. Yeah. Okay. So I haven't, okay. So I'll just share this note to the fag end. Sorry for that. Okay. But maybe like the next class, I'll just push these contents before. Yeah. So basically, like in this case, you can very well see that I have to formulate a line, something like this. And you can see this line is looking a little familiar, right? I'm not sure like whether you can, derive this line, but let's take an example. Usually a linear regression will be something like this, correct? Maybe let me go in the actual terms itself. Let's take pass category. Okay. Pass category is going to be a linear line. Okay. That's going to be having maybe a formula known as A plus B of number of hours. Right? So it's like basically derived from your normal formula, that is y is equal to mx plus c, where the x defines the number of hours. Okay. So this is the actual linear formula which I'm going to look for. But from this linear formula, I'm going to create a logistic regression, right? So I would say something like this. Probability of passing the exam is going to be a function defined on top of this linear regression. So which is going to be like number of hours. So there should be a function that derives this linear equation. Okay. So that's what this logistic regression does. Okay. So I'll go a little bit detail into it. So when you see in this particular, format, I can, certainly form this kind of a distribution by either using two, strategies. One is using logits, and another one is going to be probits. Okay, logits and probits. So both logits and probit have similar looking distribution like this. Logits is a very commonly used thing because it's a sigmoid sigmoid function. Sigmoid function, as the name implies, 1 by 1 plus e power this particular function a plus bx. Okay, minus of a plus bx. Okay, so this is your sigmoid function. Whereas probit function is something like, it is like a cumulative distribution of the first half of your normal distribution. You know what is normal distribution, right? So normal distribution will look something like this, correct? A kind of a bell curve, or I can, so in this case, the first half of your normal distribution is going to be this alone, correct? So, and you can very well see like, this is looking like another S curve. So I can either go with this logic function where it follows a sigmoid function, or I can go with this probit function where it kind of utilizes the cumulative distribution of your first half of the normal distributed data. Okay, so that's up to you to decide, but predominantly people, utilize sigmoid activation function because, sigmoid is very intuitive in nature, because I would say intuitiveness in the sense, for example, let's say you have a good control, because since you have this a plus b, okay, I have a good control of how do I, derive this line. I can, create a curve like this, or, very, very plain curve like this. All the, all the alterations I can make, I have a good control over here. Okay, I have a very good control, because when I change this a and b, okay, only this a and b is enough for me to, change anything, change the actual distribution or the curve of my particular data. So that's why people start to utilize this logic function. And not only that, okay, so only not only like logic function is only used, and you also know that, okay, basically for a linear regression, okay, let's go back to the linear regression. Basically, in linear regression, you kind of have an error calculation rate, which we kind of called as MSE, which is nothing but your mean squared error. So which is kind of a residual distance between your actual to the prediction, which is your X cap. So squaring it out will give you the actual residues. So likewise, if I calculate the residues for for this data like this, I'll be ending up with more data, because you can see this S curve is kind of bending. So which means that I have very big values here. So which doesn't make sense, because I'm not gonna formulate a line which kind of follows like this. I don't want like that. I want a distribution that kind of formulates something like this, where it is like kind of aligned together. So in that case, I definitely we cannot go with the normal mean squared error. So for this logistic regression, we use another strategy or another methodology known as log loss. Okay, I'll just teach you what is log loss. But before that, I'll just write the formula for log loss. Okay, so log loss is will look something like this. Okay, we'll discuss about this log loss very clearly when we go for this neural network, because log loss is an extension of your binary cross entropy or your normal cross entropy. Okay, I'll just write down the formula: minus y log of y cap and minus of 1 minus y into 1 minus, sorry, log of 1 minus y cap. Okay, so this is the formula I have. So basically, why do we call it as log loss is, I can, I can show you that very clearly. So for example, this y represents your actual and this y cap represents your predictions. Okay. Okay. So I can, derive this formula something like this: minimum of minus log y cap for y is equal to 1, because if y is equal to 1, this will entirely go off, correct? Only I'll be ending up with 1. So, and this will also go up because y is equal to 1. So minus of log y cap. And similarly, minus of log 1 minus y cap for y is equal to 0. Which means that like when y is equal to 0, this will entirely go off. I'll be having only this, 1 minus will also be gone. So I'll be having only minus and log of 1 minus y cap. So I can either, write this as this formula, or I can write as this formula as well. Okay. So that's one thing you want to keep. So now coming back to the topic, why do I call it as, log loss, and why do I need this? Let's take an example here. Okay. So let me draw a small box. This is the distribution which I've got. Okay. Your actual prediction. So now let's take your actual is going to be 0. Okay. And your prediction. Okay. For the given data, you are predicting it as 0.1. Okay. So now your actual is 0, and your prediction is also very close by to the actual, actual value. So now let me apply this y and y cap to this formula. Okay. I can either apply to this formula or this formula. Since I already told you, like, since y is equal to 0, I can very well go with this one, which is going to be minus log of 1 minus 0.1, which is going to be like log of 0.9999. You know that log of 1 is equal to 0, correct? Log of 1 is equal to 0, which means like log of 0.999 is going to give you a value which is very, very close to 0. So which means that Whenever my actual and prediction are very close to each other, I'll be having a very, very minimal loss. Okay. So in the previous example, in the previous class, we did saw like how did SVM solve it, right? We kind of utilize this hinge loss to reduce the loss as much as we can. Similar to that, here we use this log loss function, which is a another form of cross entropy, where I'll also try to get the very less value. So now let's go with another use case where y is equal to 1 and y cap is equal to 0.9, again which is very, very close by. Okay, now what will happen? As I told you, y is equal to 1 means I can use this function directly. So this is going to be minus log of y cap is going to be 0.9. Again, you can see like 0.9 is going to give you a value which is closer to 0. Okay, because since log 1 is 0, it's going to have a very, very closer value to 0. Now let's see whether it is working for wrongly predicted class. For example, let's take y is equal to 0, but the prediction is it is 0.9. Now it is going in the opposite direction. It is not predicting correctly. It is saying the actual is 0, but the prediction is 1. So it is giving me a wrong result. So now let's see like how the penalization works here. So for y is equal to 0, I can use this one, right? So which is going to be minus log of 1 minus 0.9. It is going to be minus log of 0.1 or 0.999 if you go, like it's going to be 0.1. So we all know that log of 0 is infinity, right? It is undefined, which means that why they call it as undefined? Because there is no literal number in the universe that can define log of 0, which means that if log of 0 is close to infinite, then log of 0.1 is going to give me a very, very big value, correct? It's going to have a very, very big value because that's like, it is closing towards 0. On another contractility, let's take the final example where y is equal to 1, okay, and y cap is going to be 0.1. In this case, I can choose this guy. So it's very evident that log of y cap is going to be 0.1. Again, it's going to give me a very big value. Okay, so whenever there is a deviation, based on the amount of deviation, my penalty will increase, because this is the maximum deviation which I can get. 0 to expected is 0, but the actual is very, very closer to 1, which means that I'll be having a very big value which is closer to infinity. Okay, so whenever my expected and actuals are very, very close by to each other, so definitely the model or the loss function is going to give you a very, very small value. Okay, so this is how your log loss function works. And log loss function proven to be one of the best method for even for neural network classification as well, because of the fact like it works effectively in penalizing the data predictions by the model. Okay, so is this clear, right? Any doubts or clarification at this point? Okay, I hope this is very sound and clear, but you'll be having one more question in your mind, like similar to your support vector machine. Here also I'm trying to, draw or divide the data by drawing a sigmoidal line or an S-curve. What if I have a three-dimensional data? So let's take a three-dimensional data, something like this, correct? So in this three-dimensional data, obviously, yes, it's not going to draw a line. Instead, we can also formulate a line which can traverse from this axis to this axis, kind of splitting this in a planar region, like a two-dimensional slice. I can also do so. Similar to support vector machine, lossy regression can also deal with multi-level features or multi-classes also. As in this case, you can see very clearly that lossy regression, as the name implies, it works very well for a binary class problem, but not very effective for a for a a multi-class model. So that's why we kind of increase the polynomial degree for the particular model. So the formula will look something like this: 1 by 1 plus e power minus, I can increase the polynomial degree, like for example a plus bx and c x2. So just use x1 and x2. So simply I can keep on increasing my polynomial degree, and I can able to address any number of classes also. So it is not, highly dependent only for a binary class. It's not like that. Yes, it can able to handle multi-class and multi-features as well. So that's the beauty of logistic regression. It doesn't require a multi it will kind of utilize the same strategy which has been employed using support vector machine, as in this case. So it's going to be very similar strategy being applied for a multi-class and for a multi-feature problem. But yes, nevertheless, we can try this logistic regression directly, in the code, and let's see like how it performs. And one more point here, which I have to like mention for this logistic regression. You can say I'm included this logistic regression function. Okay, everything is going to be the same. The only change which I'm about to do is this logistic regression function call, and that's going to have a random set of 42. Okay, so only, again, as I told you, like only 2 lines have been changed. Well, the one is the import function, and that particular import function has been called here. Okay, I'll just first run it without any hyperparameter tunes. I'll come to the hyperparameter tune little later, but for now, I'm gonna like just like that run the logistic regression module, and let's see like what's the maximum accuracy which I'm getting. So you can see that I'm getting an accuracy of 73, which is not that bad. Yes, it's kind of falling every data's. Well, even till now, we were getting the best results from random forest, but let's now see the merit of it. Okay, as I told you, this loss regression is entirely depends on the loss function, correct? So loss function in the sense like the more penalization you do, the better the model will evolve. So how does this loss function can solve this thing? Because basically the loss function will be calculated based on how I draw this sigmoidal line. So the better the sigmoidal line, the better the loss function would be, right? Correct. So in that particular case, how do I derive the sigmoidal line? So that's where I go with the solver functions. Okay, I have different solver functions. Liblinear is kind of the similar function which people use in support vector machines. Okay, in SVM we kind of use this linear function, right? So similar to that, we have this liblinear, and we also have this LBFGS. As a default, LBFGS is used, but yes, we can also use liblinear as well. I'll just show you that. Okay, I'm going to use liblinear as a solver function. And now let's see the magic. Let's see like how it goes. Okay. Let's reach 74. Again, I'm not convinced with this result. Maybe I can, penalize the model. As I told you, yes, obviously loss calculation is applied, but can I penalize it a little harder? What is penalization? We know that when the deviation is too high, we penalize with a very large number, the loss function which we have calculated right now, right? So we'll penalize the model larger way. For example, if the prediction is, so if the actual is 0, but the prediction is equal to 1, then the penalization will be like too high. But if it is very close by, if the actual is 0 and the prediction is also equal to 0, then I'll be having a very, very less penalization. Okay, so that's how penalization. But what if I kind of take a square root of this penalization? Or what if I, add some more exaggeration to this, penalization, where things will be taken even more seriously. So that's what we kind of call it as regularization. Okay. So I'm going to use, for now, I'm going to use this L1 penalty. Okay. So L1 penalty will not deal more damage. But since default is L2, L2 is one of the, more aggressive penalizer. Which means that I kind of take a square of whatever value which I get from the loss. I square it up and I exaggerate it a lot. That's what we do with using L2. But what if I go with a very less, even more lesser aggressive penalty, where in this case it is L1. Let's see how it behaves with liblinear. Okay, now you can see, okay, penalty is not written correctly. Penalty spelling is wrong. So I've utilized L1 and I don't feel like the model is performing really good here. Maybe I'll switch back to liblinear, sorry, LBFGS Again, I'll just, come back and see like how it works. Okay. Yeah. So one more thing is like for LBFGS, L2 will not work. I can go with this elastic net. This is also another, another penalty function. Let's see like how it works. Okay. Oh, LBFGS supports only L2 loss. Sorry, I forgot that. Either I can go with this L2 loss or I can even try with none. Let's see like what happens. Try with none. Okay. So it, so only penalties it supports. Okay. Maybe I guess it is this none. Yeah. So with no penalty also, I'm getting the same results, correct? If I use the Solver function as liblinear, let me go with the final round of this one. Let's get over with it. Let's see like whether we have an impact of liblinear. Okay, for liblinear penalty have to be there. Either it has to be L1, L2 or elastic net. I want to try with elastic net here. Okay. Saga, only Saga requires. Okay, so in this case, this penalty for liblinear, either I can use L1 or L2. Okay, so L2 is a default. If I can use L1, like what I'm getting it here, right? So likewise, okay, so the maximum accuracy which I've got here is like 74, which is not, a really great accuracy, I would say. Yes, loss regression, kind of, meet 74% as the maximum accuracy which it can able to create. But you'll be wondering, what is this liblinear? What is this, LBFGS, SAG, Saga? There are many different solver functions, which is very similar to gradient descent. Okay, so you'll understand about this in detail when we start to learn about this neural network, which I'm going to take it the next class. But simply put, LBFGS can be utilized for a large data model. Okay, if you have more number of data, you can very well go with this LBFGS. Okay. But if you have very short and crispy data like this, for example, you only have like 700 data, right? So if you have only 700 data, then definitely then you can very well go with this liblinear. Apart from that, we have Newton, CGS, Saga. There are many different solver function, but personally, I kind of utilize only LBFGS and liblinear. Both usually gives us a superior outputs respective to the data given. Okay, so this is about loss state regression, guys. So everything is going to be the same here. The only thing is like I've changed the function and I'm just playing with the different hyperparameters. So it's all about like how do you play with these kind of hyperparameters. The more you play, the better understanding you'll get, because it's all about experience. You once you start training data or start training models with different data set, you'll get a very good essence of what really happens when I change this kind of this kind of hyperparameter. So like you'll gain a good experience out of it. Okay, so that's one more thing which you want to keep in mind. So I hope this is very clear. Are there any doubts or clarifications? Okay, so I guess there's no questions. Let's go for the next topic. So till now, okay, from day one, we were looking on to this basics of Python, statistics, all these things. We were listening to it. So right now, I would say you have gained a good experience in how does a machine learning model works. It's all about the algorithms. But even though the algorithms are there with scikit-learn, how do you prepare the data? Preparing data is very important, guys. Okay, so the way you prepare the data is very important, because once the data is segregated very properly and neatly, in this case, I have segregated it correctly and I further split it down, drill down to training and testing. So if these data are handled properly, then your ML output will give you, tremendous values, because scikit-learn, it handles a lot of ambiguity, inside it, because no matter like what kind of label you have, no matter what kind of data you have, it is a float or a string or or an integer, it doesn't matter. Scikit-learn converts and scale it down as per its functions. So which means that creating an ML algorithm has become a very, very easy job nowadays, because you don't want to worry about anything. The only worry which you want to keep here is the data itself. How do I extract the right data? How do I, split the data into input and output? So if you can able to do that correctly without, without messing that up, then definitely you can go with any any functions inside scikit-learn. As I told you, you can very well go to this documentation. This has all the examples you need. Okay, so basically it has, you can see, right, by clustering, calibration, classification. If you go inside classification, we have different types of classification techniques. Like, okay, so there's a comparison of several classifiers. You can see, right? So people can run this function. So basically what they've done here is, like, you can see they have kind of added all the classes, all the different classifiers together, and they are going to run, and they're going to run every classifier and see like which one works better for them. Okay, likewise you can play with it. You can very well play with it. And they also have this, you can also download the source code or an IPython notebook, and you can run it on your one. And even you have this launch function where you can, I guess, you can run this out um, directly in a kernel, and you can try it out with your data as well. So basically, the scikit-learn has a very good documentation, and they are covering all the important algorithms provided. So I would recommend you to look onto this documentation, and try to take the fullest out of it. Okay. So if you have any other doubts or clarification, yes, we can clarify it now. But if not, we can very well go for the next concept. Okay. So since there are no doubts, we'll go for the next important topic, the session. That's your natural language processing. Okay. So, okay. Okay. Sorry. Yes. So the important topic is natural language processing. What is natural language processing? The way we talk is also a language, right? We talk in English, we talk in Hindi, Tamil, Telugu, Kannada, Malayalam. So there are many different languages. But as long as you can able to communicate with anyone, okay, that's what language is all about, right? Because if you can able to somehow pose them, somehow make them understand with your words, that's what a proper communication will look like. So you are trying to give the right meaningful words so that they can able to understand the essence of it. So that is your natural language. So naturally, whatever which you are doing is kind of a language which you have created. So I'm going to utilize this natural language and try to put some sense to my actual AI. Okay, because the AI doesn't understand how do you speak. Okay, so it's not numbers, it's words. How do I convert these words into a number? All these kind of changes, how do I do it in a way where my model can evolve really great? So that's where natural language processing comes into play. So yes, imagine this particular sentence: a smiley followed by a keyword, or a reply known as okay. So just relate this particular reply for different sentiments. Okay. Sometimes people utilize the same, same line with a smiley and the word okay when they are very happy. And sometimes even when they are very sad, they can also put it. When they are very angry, yes, they can put the same smiley and followed by okay. For every single emotion, okay, I can utilize the same smiley followed by okay, and that will literally make sense. Agreed? I guess like many would have faced this particular problem, like boyfriend girlfriend issues. Usually, when you have a fight, you will never understand like what this mean. A smiley is a very dangerous utility nowadays. So literally, it has like 1,000 meanings. One single smiley can have 1,000 meaning, whether they are angry, sad, disgust, or happy. It can be like it can be any meaning to it. But okay, so somehow that particular person, and the previous conversation of that, and you might have a guess, let's say, okay, I've scolded him or her. Okay, maybe that's why he is giving the smiley, so maybe he's very angry at me. Or if you are an argument, and if the smiley comes on, there's no reply back, and you'll be like, say that, okay, they are very angry, so I have to, like, console them or something like that. So likewise, the context of previous data, and you can able to give some meaningful insights to it. But let's take a system that can only understand this as a number. So for this particular smiley, I'll be assigning a number. Let's say for the smiley it will be like 0, and this for, okay, I'm gonna have it as 1. So if I have the 0 and 1, okay, so I'm gonna say it as positive. The same 0 1 is going to given for negative, and bad, all emotion, all different points, I'm giving the same values. Now if I teach my a baby with the same logic, like let's say I'm giving a smiley to it, and the baby says, okay, so you are feeling happy, and I'm saying, no, I'm feeling sad. Now the baby will be confused, correct? So now, which means that with this natural language processing, understand the nuances of the content is very tough, unless and until you know the previous contents. If you are little aware about the previous statements which is provided, then yes, you can somehow make a decent understanding about the text. But nevertheless, it is not an easier task for the model to understand. Yes, human beings sometimes also fail to notice the sarcastic meanings behind it, right? So that's what. So basically, having having an engine that can able to understand your natural language is very, very tough. And you will be wondering why ChatGPT is very famous. It's all because of its wonderful algorithm that can, or that that has an ability to understand your language very clearly, or your motive very, very clearly. So that's the advantage. That's why it became very famous. But nevertheless, how did they achieve it? That's the point, right? Let's go a little bit in detail. And also, sometimes people use how are you, or they simply use HRU, correct? I guess many, not many, everyone would have used this terminologies like HRU, what doing. You will never use a proper grammar or sentence, like WHAT, what are you doing. You have to, like, ask in that way. But you just put what doing, good night. Sometimes people use GN, or sometimes people use GN8. For weight, they'll use WA. There are different keywords, different word formations, which only you and your friend will understand. So which means that if you're going to use the same language to a language model for a natural language processing, how do I process it? Because W and 8, it looks like a formula to me. Okay, as an ML engineer, this can be a weight for a neuron. I can think in that direction. If it's a chemistry professor, or if is a chemist, you may be like looking into a different angle. So likewise, everyone looks in a different angle. So like, how do you want your model to evolve? And how do I handle this kind of different, or tough words which is only applicable for your friend alone, or something like that? So how do my model evolve? So this is a very tough challenge, agreed? Because when it comes to language, you can communicate it in number of ways. If you want to say a sentence that I'm feeling really good, you can formulate the same emotion with different words or different scenarios. Infinite number of possibilities are there to form it. So which means, like, how do my model generalize here? Because for numerical data, it is fine. I have numbers, I have the fact sheet with me, I train a model, I get the result. But here there is no fact sheet at all, because people can ask how are you, or people can even ask HRU, or have you been doing, or are you okay? So there are many different ways of approaching the same question. So how do you how you're going to approach this? But deep dive into, like, how and what, I just wanted to show you one simple thing known as encodings. Because as I told you, no matter what, AI handles only numerical data. Okay, as long as it is a numerical data, it can able to handle. If it is a text, definitely it cannot handle, because text are literally something, a different entity only human beings can understand. But AI only understand in form of text. Your system, your computer handles everything in binary format, like zeros and ones, right? So all the numbers will be an important factor for your AI model. Which means that, how do I convert my words or characters into numbers, which is giving me the right meaning, or which gives me the right meaning for the model? Okay, so that's very important, because let's say if I don't give the right numbers for the words, maybe I might be ending up, making my model not learn correctly. It's like, when you go with the tabular column, for example, let's say for high, I keep it as 1, and for how I keep it as 2, and for h I keep it as again 1. So this doesn't make sense, because for high and h, if it is same, then my model will be more confused. So the word embeddings is very important. But initially people were having this in mind. So because like giving a number to a word will be like more ambiguous, because there are infinite number of words. How do I derive all those words and create a number for it? That's going to be very, very tough, correct? So that's why what they taught is, what if I encode the characters? In this case, you can say I'm just giving a random number for every characters in my in your ASCII 32, or sorry, ASCII format, or UTF format, or Unicode 32 or 64 bit format. So for all the characters it's available, if I can able to give it a number, yes, that is also a possible way, because very well I can get these numbers up and running. But there is a problem. You can see, right? Silent and listen have the same amount of characters. If when you like look into a character level, S and S is here, I and I is also here, E and E is also here, T and T is here, N and N is here, and L and L is here. So which means that silent and listen have a different arrangement of characters, but it has the same characters. So which means that if I don't see it sequentially, my model will fail. If I look at it as holistically, then for me, for the model, I mean for the system, both the numbers are very much the same, because it's only the arrangement is different, but the numbers are same. What if I add this number together, or what if I do some operation which is position independent? In that particular case, this particular embedding will fail miserably. Agreed? And it is and again, it's going to be very tedious. If let's say if I have 1,000 words, and each and every word have 10 to 15 characters, obviously I'll be ending up having lot of numbers which I have to store into my memory. And again, that is also a bigger problem. So that's why people think that, okay, so yes, ambiguity will be there, but this is the best bet I have got for now. So which means that what people derived is, what if I create numbers for each and every word? Okay, in this case, you can see that for a sentence, I love my dog, I for I it is marked as 1, for love it is marked as 2, and for my it is marked as 3, and dog marked as 4. So basically, this particular words is new for the particular system. So I'm whatever new words which I get, I formulate, I go on create different numbers to it. For example, when I get a new sentence where I have same sentence like, same sentence like, I love my cat. So since I have already tokenized or already created numbers for this word, I love my, I don't want to recreate different number for the same character, I love my. The only new character, the only new word which I've got is this particular word cat. So I can go and formulate a new number for it. Okay. This is one way of doing it. So obviously giving numbers to all the words which you literally see. So if my model is going to be trained, okay, where it has to interact with a human being who has a very limited vocabulary set, let's say a 4th standard student. Obviously, 4th standard student will not be very, very vocabulate. He doesn't know many different, English words. So which means that like he'll be using or will be forming a very basic sentence, something like that in English. So in that particular case, yes, I might have a limited vocab set of 1 lakh words. That is more than enough for me to handle this data. So I kind of create these numbers in a way where all the 1 lakh numbers have been taken and tokenized with the number. So in that way, yes, word based embedding or encoding can be very ambiguous in nature. As I told you, like you have to go through all the possible words which you see in the world. But yes, even though it is tedious in nature, it provides better results. And people, even large language models or your chat GPTs, right? It kind of utilized, you will be like surprised to see the number of words it has utilized to tokenize it. It is like it has reached like 50 billion words. There are like billions and billions of words which has been taken and which has been tokenized by the model so that it can able to understand every possible word, which means that it knows the difference between love and loves, or sorry, love and lover, because love and lover has the same content, right? Same characters, only one extra word has been created, which means that it should have a different number for this and it will have a different number for this. Similarly, like if I use how are you and h are you, okay, this have to be closely mapped against it. So which means that there's one more problem at stake. For example, I can address a woman by saying that girl or that woman or queen, wife, girlfriend, or GF. There are many ways of addressing a girl, correct? And her, yeah, I can also add her. Similarly for boy, I can say it as man, boy, maybe king, prince, boyfriend, him, or his. I can go and formulate many different words that points towards a gender, or points towards a subject. So now in this case, how do I give numbers for this? Because all these are very closely related. Sometimes I can say something, so I saw a girl, okay, I saw a girl who lives next to my street. And I can also put a word, I saw a woman who lives next to my street. So like both the words or both the sentences doesn't doesn't give any contextual information about what's the age of that particular girl, but they're just saying there's a gender, I mean woman gender, a woman is living across the street. That's the essence of it. So which means that both the sentence conveys the same meaning, correct? Unless and until they kind of I saw a girl who is similar to my age. In that particular case, okay, so I can give a contextual information about his age. In that case, I can go with girl or a woman, or or different entities of it. Which means that yes, sometimes different words formed inside a sentence can have the same meaning. So now comes another big dilemma, right? How do I tokenize this? Now, since you have given me an idea that yes, I can formulate numbers for each and every word which I come across, that was an impeccable strategy. But now, when I form these words closer to a sentence, everything changes, correct? I can also even give you a better idea. Let's say I love my dog. Okay, this is one question. He looks like a dog. Okay, he looks like a dog. So now this function, or let's say this sentence and this sentence is totally different, because here you are subjecting to a dog, but you are subjecting to him, someone, or maybe I can give a name known as Alex. Alex looks like a dog, which means that I'm subjecting him and not the dog, which means that in this case, obviously for this dog and for this dog, I'm going to have the same number as 004 and 004. But when it added to a sentence, this number will not create a good thing, because here it is subjective. Here it is kind of it's not subjective in nature, because Alex is a subject. So the entire subject is changed here. So likewise, you have many different problems in a natural language processing. So it's still now, I would say, word-based encodings are being utilized till now, but they have a different possibilities to come with. So one more possibility, as I would say, is like the transformation of your sentences. Sometimes if you're not finding the right essence to your model or the application, you can represent the sentence. For example, it is the best of the best. So what I can do is I can count the words which present. For example, it is the best of, and so these are like individual unique words, and I have two best here. I don't mind about that. I'm going to see like what are the words present here, which means like this best and this best is going to be considered as only one single word. So which means like I have it, I have is, the best of, I don't have a, and I don't have an. Okay, so this is the information which I'm getting here. Okay, just counting the vocabularies alone. But what if I take the frequency of it? For example, it is the best of the best. I have two the and I have two best. So I'm going to increase those numbers for the and best. I'm going to count into two. So it's like frequency counting. So either I can represent my sentences in a different feature, right? Because the different feature which I construct, yes, I can, or I might have a good possibility of understand the sentence little better. This is one way of doing it. But nevertheless, the best method which was evolved in 2013, which we kind of called as word to vec. Okay, so basically what they did is they kind of started building a very, very, very big corpuses. So where they did it, like they kind of combined all the data or all the possible words, and they started forming groups. For example, you can see father, I'll just say queen, mother, king, man, cat, cats, dog, dogs, Paris and France, London and England, Rome and Italy, he, himself, she, herself, long, longer, longest, father, girl, son, mother, boy, daughter. So no, these are like some relations, and this is also relation together, and this also have some relation. So all these words have been taken and have been grouped in a way where the similar words have been like forming together. You can see father, boy, father and boy is close by, and also father, girl, and son is close by. So boy and son is also close by. So I would be like also having this mother, queen, girl to be close by. So this girl can be can be given here. So this girl can come here, so that all these woman gender is kind of close by, daughter, everything is kind of. So, and again, fathers and boys kind of close by. So likewise, people created a very, very large corpuses. This is what now have been evolved as large language models. So whatever this LLMs, because LLMs is the basic essence of your chat GPT, right? Because GPT requires all the linguistic proficiency. So all the linguistic proficiency, the vocabularies have been taken from these large language models. So basically, this word work was a stepping function for your for the evolution which we have right now. But I would say nevertheless, even though the superiority have been given ChatGPT as a good AGI, artificially generalized, but till now word work is being considered as your vectorization part, because ultimately when you have a sentence, I have to convert into a vector, that is basically your numbers. Once the numbers are formulated, only I can able to do something out of it. So which means that yes, people still are using this word to vec. Okay, so they have this word to vec, they kind of closely arrange all the words together and they kind of create a number. So in this case, the number will not be just one single number. Okay, it's going to be a 64-bit number. Okay, it can be it can be a 32-bit number or a 64-bit number. So it's a 64-bit number representation, so that the model will find it very easy to proceed with, because that for every models, always it is better to have it in the form of float, because float values have good precisions, which makes the model precisely tune the data very effectively. So that's why even this word work is kind of maintained in a 64-bit embedding format. So each and every word when you call, you have a 64-bit number. But yes, you can drill it down to 32-bit also if required, but it's based on the language models you have. So basically this is kind of called as corpuses. Okay, you have bigger corpuses, and now people are calling it as large language model, where all the languages are being taken, all the different conversations, words, connecting dots together. All these things have been formulated by a group of team, and they kind of released it. So this large language model is publicly available. Anyone can use this large language model, and they can create their own vocab set or or a word vector, something like this. So that's the essence, or that's the evolution when it all started from this word work, because only with this word work people had a more refined way of featureizations. Okay, the way they extract feature have become little bit refined, where the closer components will have the bits or the values which is very close by. So also it will be very unique against each and every word. Sometimes it will be something like this. For example, I'm just giving you an example here: slow and slower. Okay, so both are almost the same. The only thing is like the tense is different. So maybe my number for slow is going to be like 1 point, or maybe like 0.0000010. Okay, and for slower it's going to be like 0.00011. So there's only one precision bit got changed. Maybe if it is like in the 10th position or 20th position or 64th bit position, there's a huge or a very very small difference which is provided, because slow and slower is very close by, only very small deviation in the understanding. So maybe I can closely associate my precision values in a way where the words have been combined together. Okay, this is what we call as feature extraction. Basically, feature extraction can be can be done for any data. So the idea behind feature extraction is to reduce the semantic gap between human being and the systems, because human being can able to understand things just like that. You don't want to have a word vector for here, because father, son, boy, or father, son, king, all are coming under one category. So without creating any models in your mind, without any word vector, just like that, our human beings can able to do that. You don't want to code anything in your human brain. But for system, it is totally different. I told you, like, it will be having only in the form of numbers. So how effective the numbers defines the model development. If the numbers are very not straightforward, it's not doing a really good value to the model, then definitely the model will not evolve. The model will get stuck at some point of time, and it will go on and on and on and on. Okay, so this is how word vector came into play, and which is effective, which has a more effectiveness nowadays. And apart from that, that's fine. Okay, so I have word vector, I have some some sentences. I can use the sentences, convert it into word vector, and I can able to process that. I can do all these things. But is that really enough? For example, I just take two questions. What are you doing, and what doing? So obviously, okay, both these sentences have the same meaning to it, correct? Which means that the focus or the attention which I want to create is onto this what and to this doing. I don't want a question mark. I don't require a comma, or sometimes you use where and weren't, don't, or do not. There are different words. So there are some pre-processing which we can do for a text as well. Pre-processing is a very important step for any case, because you cannot give the data in raw to the model just like that. That will be like maybe it doesn't create a good model. So it's always better to sanitize the data. Again, how do I sanitize this data? By removing the unwanted words or something like that. For example, in this case, I don't want this "are you" at all, because once I know this what I'm doing, I know the actual question. Likewise, for each and every word or each and every sentence, there might be unwanted contents. So for example, I love my food. In this case, I love food is also fine. And let's say I love chicken. In that case, yes, obviously I love chicken. For all these three words will be important, because I cannot remove anything. So likewise, sometimes this off, some stop words are there. For example, because, but, is, was, with, her, all these kind of non-lexical words are not really important to me. Okay, so how do I change those? How do I pre-process those? So that's why we kind of create different NLP strategies to make it more effective. Instead of relying onto the language models, yes, it can do a good favor, but before you push it to a model, it is always better to pre-process it in a better way, so that the model will have even more better accuracy. Okay, so there are some concept on a sententizer, but before sententizer, we have a concept of tokenization, because tokenization is very important here, because for every sentence given, I have to convert into word by word. Okay, I will be converting to word by word, and for each and every word, I have to convert into a vector. That's your word by vector, or any number, any local number which you're going to create, that can be done. So the first and foremost step is to tokenize the data. So whatever sentence or whatever paragraph or whatever book you're going to give, I'm going to read all the words and collect the unique words from there and tokenize it. So that would be the first step, the first and foremost step which will be created. And sometimes you have to split the paragraph or a very book into sentences, from words to sentences, from sentences to paragraphs. So that's up to you to decide. But anyways, I can pre-process it in a little different way. Instead of sometimes instead of me giving a very big sentence to my language model, and giving sentence by sentence will make little bit more sense, correct? So likewise, I can create or divide the sentences and I can process it one by one. And sometimes I know this case, run, runs, running, and runner. In this case, run, runs, running is almost the same. All these three are defining to one action, run. But this runner, shows the subject, which means like, this is regarding the subject. Someone is running. So this is different. But this run, runs, and running are almost the same. That's what is we call as lemmatization. And as I told you, like stop words, some stop words like, off, it, um, because, but, something like that. So all those stop words can be removed because that doesn't create or add more value to your actual understanding of the content. And we also have this parts of speech, dependency parsing, and I'll also show you like how this word vec works as well. So for this to process, there are different libraries which is available, guys. So we have NLTK, we have TensorFlow, we have PyTorch, we have even Keras. But for this case, I'm going to use Spacy, okay, because Spacy is a very intuitive and a very easy tool, because the beauty of Space is like they already have a language model with them, which means that they already provide a very large language model, then where you can directly use that to to do any works as per your wish. Okay, I'll just go to that folder. Yep. So I'm going to open the first program. I'll just teach you like how this usually works. And one more point to it is like, I'll also share this. If you want to run these programs, you might need to install this Spacy library, and you might require this wheel file as well. Okay, EN core web. So this is the language model which I'm talking about. So it's like a 13 MB model that might have some like maybe like a millions of words. But imagine this language model itself have been in GBs as well, which means like how many billions of words it would have handled. So that's that's a key thing. Okay. Anyways, I'll just go for the first program. Okay. So what I'm going to do is like I'm going to like import this function known as from spacylang.en import English, because I'm going to look for only English words or characters, and I'm going to like initialize my object NLP is equal to English off, because English is going to be the the function which I'm calling. This NLP is going to be the object. Now I'm just going to create a very small text. Okay, so when learning artificial intelligence, you shouldn't get discouraged. Challenges and setbacks aren't failures, they're just part of the journey. You've got this. So this is the sentence which I've created. Okay, now my first and foremost thing is to tokenize it. Okay, how do I tokenize it? Basically, I'm going to call this function NLP of text. I'm going to give this entire text into this particular object, and this will create a a doc variable or a doc object. With this doc object, it's not an object, it's like kind of a list actually. Okay, so I can directly call this my doc, which will show it in the document format, the similar format which you see here. And I can also use a for loop to go word by word, like token by token. So basically, when I call this NLP of text, it passes all the data. Okay, so now the interesting fact is like all the first step is also be considered, this entire word will be considered as one single word. So that's the point of tokenization. So you should not be like considering just two words, either should and not. But yes, you can also create a one tokenization where you can include or divide this should not into two words, should and not, are not, aren't into two words and are not. So let's see like how this works. Okay, so I'm using this Spacy's tokenization function. Let's see like how this tokenization happens here. Okay, so I'm going to run this guy now. Let me go to that particular path. Let me run it. Yeah. So I'll just zoom it a bit. You can see that document format. This is how the content looks like generally, right? So when learning artificial intelligence, you should discourage chances of failures. Blah, blah, blah. So now when I convert into tokens, this is how it looks like. Okay, you can see when learning artificial intelligence, comma is taken as one token, because I'm literally taking everything as token, because it's not like I'm gonna like how to say, like I'm gonna like leave behind this stop word. It's not it, because this is the first point. I have to tokenize it, and then only I'll be I'll be making sure whether or not I want this or I want this particular word or not. For example, if I don't want comma, I can remove that comma using stop words function, which we'll be seeing a little later. Okay. But you can see as an interesting fact here, you, should, and not has been separated as two different words, which is good, right? Because sometimes people think like, yes, it is two different word. You can keep in that way itself. Shouldn't is just a fanciness which you give to should not. Shouldn't and should not will give you the same meaning. So it's better to have it as two separate words. Similarly, get discouraged, and there's a first, this exclamation is taken as one token, even the slash n, your next line is taken as one more token. So all these tokens are into considerations. And you also see you have, this have is also been separated separately, and they aren't all these words have been separated, and they kind of made sure all the words are separated and tokenized correctly. So that's the beauty of Spacey, because they can able to handle it a little better. Okay, that's fine. This is tokenization. That's fine. Let me go to sentence. So I'm going to use a function known as doc.sense, because this particular object which I've created right now, it is an object. I can traverse into it just like that. That will give me the tokens. If I just print it, it'll show the exact document format. But if I want to traverse sentence by sentence, yes, I can do that. By calling this attribute or the method doc.sense. If I call this doc.sense from this object which is created from this input text, I can traverse sentence by sentence. Okay, so everything is the same here. Like the only thing is like I'm gonna okay, this is not required here. Okay, so yeah, so yeah, one more thing. Say you can see there's one more catch to this thing. So this English is a function or a method which is loaded and an object has been attached to it, but I have to create a pipeline for sentences alone, because sentences is a separate entity, because sometimes you might be having slash n, sometimes you might be having this this exclamatory or question mark or full stops, or sometimes you may be having full stops in between the sentence as well. So this is a separate pipeline which you have to create. So for that, I'm just creating this pipeline component, and I'm calling this adding this SBD object into it. And then after that, when I call this function, I get this specialized attribute doc.sense. Okay, so now let me run that. You can very well see like how the sentence have been created here. Okay. Okay, there is a problem here. Because string name of registered component factory, not a callable component. Okay, so what we'll do is, let me come on these guys. Let me see like how it runs, whether it runs or not. So I guess like the versions which I have was little old, maybe that's why like it's not working. Okay, I'll just update this code after this call. I'll just give it to you where you get the sentence as well. Okay, so basically like this should work in Google Colab. I'm not running it there. My local, there can be like some certain mismatch in the versions as well. So I'll also certainly give you the updated code or the updated version which you have to install for Spacey. Okay, so that's one thing. Let's go for the next one. The next program is going to be the stop words, which is going to be very exciting here. So as I told you, okay, so I'm going to use the same sentence here, but in this case, I'm going to like use this function on a stop words. The stop word is like a it's a very basic list. Okay, so they have created a list that has all the words that is not really required, which we call it as stop words. So basically, you can see here, right? I'm going to like show you the length of how many stop words I have, and I'm also going to print the first 10 stop words to just show you how these words looks like. Okay, and then as usual, I'm going to load my function, create a sentence, and then what I do is like I just use a small condition, like if word is stop. Okay, if the particular word which I'm traversing, the token or the word which I'm traversing, if it is a part of stop word, I'm gonna like come out of that. Only if it is not inside the stop word, only if it is not as a part of stop word, then I'll append those words alone. which means that I can filter that. It's a very simple if condition, guys. Okay. So stop word is nothing fancy here. I just have a list. That's all. Stop words is a very big list which people have collected, and they've meant that, okay, this is the words which I have, which I want, and that can be possibly a stop word. I don't want to require any end user to create this, number of words which they feel like it is, wrong or wrong or correct. In that case, this has already been defined inside the function spacey itself. So I'm going to utilize that. The only thing is, like, it's the list is created, I'm going to use if condition to see like whether the particular word is belong to a stop word or not. If it belongs, I'm going to pause it. If it doesn't belong to the stop word, I'm going to add it to the actual sentence. Okay, so now let's see like how it works. I'm going to run code program. Okay, so now you can see the number of stop words which spacey utilizes is 326 stop words. And you can see these are the stop words which is not required, or maybe like, ruled out by spacey: been, myself, above, my, must, to, everything, hence, what, why. So all these words have been considered stop words. But if you feel like, these words might be required, for your model processing or training, something like that, yes, you can, neglect it, something like that, because basically this is a list. Once you get this spacey stop words, you can, add or remove, or even you can add it. For example, I don't want this exclamatory mark, I can very well remove it. You can see like the filter sentence have this: learning, artificial intelligence, discourage, challenges, setback, failure, journey, got. That's all. With this number, with this, limited sentence, I can able to form a good insight to it. Because yes, even this might sound a little odd, but it has all the meaning which we are looking for. It's like a simplified version of your sentences. So lesser the contents or lesser the word, very less confusion will be created for the model. As I told you, because when you go with this word work, you should forming all the words for closer meanings and stuff like that. So when you reduce these kind of words beforehand, before you push it to this word work, then yes, this is a very intuitive way of doing it. So as I told you, like, yes, you can include more stop words if required, or you can even create your own stop words, just a list. That's all. You can just very well create a list. Spacey stop words is equal to some words like this, something like that. That's also possible. That's up to you to decide. But yes, if you want to go under the hood, you can call this particular function. Okay, is this clear? Any doubts or clarification at this point? Okay, so since there are no doubts or clarifications, let me go with the next function known as lemmatization. Okay, so as I told you, like, if we have some different meanings, or same word that has different words that has the same meaning, I can remove those things. So for that, I can use the command word.lemma. So I'm gonna mm, call this function known as lemma. That's more than enough for me to print the word. So let me run that right away. I'll just show you how the result looks like. So you can see, right, running people and peoples, there is no lemma at all, which means that there is no other alternative meaning at all. So yeah, so this can also be a reason, but I would say, like, ChatGPT is more evolved right now. Okay, because yes, if you feel like some unwanted words can be taken out, yes, you can remove those. You can stick to the right prompt. But it doesn't matter now, because it has evolved a lot, because it has been learning from a lot of data people which they are speaking since. Because whatever which I'm teaching you is the very basic of NLP. Okay, whatever ChatGPT is there, it's like a large language model. It has transformers. It has a lot of fancy architecture, which is kind of creating the model to be better. But yes, you can also keep these ideas in mind. If at all future, if you want to prompt it correctly, yes, you can keep these a few pointers in mind. But nevertheless, don't worry more about prompting, because prompting is way more easier than you think of. It's all about getting a right knack to speak with it. When you first friends, when you become friends, for example, you and your friend, you might not know like how to properly communicate with them. But slowly, once you grow together, or work together or study together, you kind of have a good feeling of how your friend will react for this kind of sentence or something. So you will be getting a good bonding. So like how to communicate with them very clearly. So likewise, ChatGPT is all about experience. And yes, there are certain manuals to it. Yes, we'll be discussing more about the later, or the back end of the session, where I'll teach you like what kind of prompts can be utilized to make it a little better and better. Okay, but anyways, in this case, the lemma is not there, because sometimes for words there'll be like no lemmas at all. So likewise, you can use lemmatization to see like whether there's a lemma word. If there's a lemma word, I can replace that with the common word, something like that. Okay, so that's one more thing. And apart from that, yeah, parts of speech is not widely used nowadays. Okay, because because of this word vector being evolved very great nowadays, like parts of speech is not really required. But sometimes you might be having a very specific requirement to check the grammar of it or something like that. In that particular case, then you can very well use this word.pose. Word.pose will give you the exact grammar POS tagging will be created for it. I'll just run it. You will get a good idea about it. It's like parts of speech. So I have some text given. Okay, so what is the text I've used here? All is well that ends well. So for all, I use some DT. E is auxiliary, well is adjective. D again DT, verb and adjective and punctuation. So you can see like I get a parts of speech. I don't know like what is this DT. I'm not good at English, but anyways, so you get the parts of speech. Sometimes um, these parts of speech is also sometimes will be utilized, not every time, because as far as I know, like in large language models and GPTs, we don't look for the grammar. It's all about the sentence we have. More sentence we give, better the model will evolve. So it was nowadays correct. Your sentence grammar list it might be using. Yes, they might be using this POS, but that's what I'm saying. So previously, like 5-6 years back, people were utilizing these kind of strategies known as POS or something like that. But now we have we have models that can able to handle large amount of data, which means that I kind of type a ground truth. For example, am I doing a good job? That's the ground truth. And all the possible wrongly spoken sentence, for example, I'm doing good, I'm doing job, am I, or not using the right verb or not using the right adjective or something like that. In that case, I can create n number of possible wrongly written sentence. So I can give this as a ground truth, and that as a binding word to it, like a translation to it. So in that way, the model can also evolve. Yes, you can also utilize this POS as well. Obviously, as POS can also help you out. A rule-based method can easily make this work. Or else, if you want to make it make it more robust enough, then definitely you have to go for a very, very bigger data set, or a transformer based model to do it. That's one more point to it. Okay, apart from that, yes, we also have this word vector. I'm going to skip to this dependency parsing. Okay, I'll just teach you what is dependency parsing in the first place. Sometimes we might need to know like the entire sentence, which word is being dependent on which word. For example, President Trump is there. In a pursuit of all, President Trump ran into one. Okay, so this is a sentence I have. So what I do is like I'm gonna print the text, the root text, the dependency, and the root and head text. So I'm just gonna print these four things. Okay, the actual text, the root text of it, and what's the dependency of the root text, and what's the head text for the dependency. So I'll just run it. Maybe you will be getting a good idea about it. Okay, I'll just tell you about that. Yes, so you can see here for pursuit, the object is is like dependent about the sin. So basically, I'll just keep the code side by side. You can see first is the text, second one is the root text. The normal text is the root text is wall, and the dependency is also the wall. Okay, that is the object which is like referring to, and the next set text is going to be off. The before A, it is off, and after it is a wall, and that's a dependency text. And similarly for president, the actual word president, the dependency text is Trump, and the object is also Trump. The Trump is not an object now; it's a subject. And what does the subject do? It is running. So kind of a dependency plugin. So we kind of take a word, we see like what is a preceding word and what is the word, whether it is a subject or an object or something like that. Based on the objective, what is the dependency word or something like that. So in that case, President Trump ran. So in this case, Trump ran. So the actual subject is Trump and it is running. So I'm getting some more different insight about it. So it's like combination of POS and parts of speech and dependency passing together. But to answer your question, let's say if you are training a book recommendation model, so how Spacey and Anaconda help us out in what ways? So basically what we'll be doing here is we'll be using Spacey to remove all the unwanted words. Okay, so if you're using a book recommendation, obviously, a book recommendation is based upon the book name or a context of the book and the sentiment to it, yes or no, something like that, or maybe giving a genre to it, action, crime, drama or something. So in that case, I'm going to give a very short sentence about each and every book, and I'm going to have some labels to it. So in that case, all the short sentences can be, cleansed, can be cleared in a different way. And I can also create a word vector for it. I'll just show you the next program where I'll be creating a word vector. I'll just first open the program. Word vector. You can say I'm going to create a word vector for this word mango. Okay, let's see like how the vector comes out. You can see this is the word vector which I'm getting. At 32-bit, I guess it is 32-bit, 6. No, it is 64-bit word vector. So basically for the word mango, so it's like not 96-bit. Sorry, it is like 96 vector values. Yes, I can change this. I guess for Spacey, it is like fix it to 96 numbers. Okay, so if I change the mango to mangoes, okay. Yes, the number will be a little different, but somehow it should be related against each other. Okay, so because as I told you, like this word vector should be like aligned in a way where all the closest meaning text should be forming those number close by. Okay, so in this way, so when you want to create a recommendation, obviously you can use Spacey, you can get this kind of word vec, and I can push it to a model for learning. Let's say your scikit-learn's support vector machine or anything. So all I want to do is convert into number, convert all the sentences or all the words into numbers, and once you get those numbers will be acting as a feature. So you have features in the labels. So basically you can push it to a decision tree algorithm or any algorithm. Okay, so let's say you have support vector machines, you have random forest, you have boosting, you can go with any kind of models to train them. Just like that, you have the input and the output. But for the input, you're going to do some pre-processing and making sure that there is no stop words and there is no lemmatization which is involved. So making sure the words are being cleansed out very clearly, and then they kind of you can push it to a model training. But if the word is not cleansed properly, we might have the same words coming in in and back out. For example, I would say, let me take two sentences here. Sentence 1, which is giving a horror context. It is very scary. Okay, I'm going to say it is very scary. And sentence 2 is a comedy genre. It is very funny. In this case, you can see when I train this model just like that, what really happens. We have this very and scary, very and funny is very important to me, but this it is not required because it is kind of occupying. It is kind of giving me the duplicate values for both the sentences as in this case. This will create a lot of dilemma for the model itself, which means that the model will be confused with this kind of common words. So if I use Spacey very effectively, I can remove these stop words and I can remove all this non-lexical fillers where I can focus only on the context. What is the context here? Scary and funny. Maybe very can be maybe sometimes useful because it is giving more weightage to the current book or something like that. Let's say scary and very scary. In that case, this is not required to me. So likewise, we can use Spacey and we can use this kind of support vector machine or any kind of ML models to train it on. Okay. So yeah, you want me to run it for mangoes? Yeah, yes, we can do that. That's a good way of. So basically, so no matter like what word you're going to use, it's going to create a unique word vector. but it's very little. It's tough to compare it against all the 96 numbers. But yes, obviously I would vouch for this, because all the numbers, or at least like few of the numbers, will be a little different against each other. So but making sure there's a close relations towards against each other. But in this case, mangoes and mangoes is totally different. This is how NLP plays, guys. This is what I want you to experiment all about. Okay, so just try to run this kind of word vectors and see like how many what's the difference between each and every word. Take this list and compare, or maybe do a negation with this other word vector, and see like what's the difference and what's the magnitude of it. Likewise, we can make it we can understand like how these word vectors are being formed. But I would say, nevertheless, yes, this can be utilized for a simpler task. For example, you have very less sentence, and when you have very less content, yes, definitely you can use it for a simpler task. But when it comes to a generalized model like chat GPT or something like that, in that particular case, you have to you cannot rely with this particular data model. Obviously, you have to go with a larger language model, so which will be like covering, which I'll be covering a little bit detail when we enter into neural network path. So is this clear? Any doubts or clarification at this point? I hope I've answered all the questions. Okay. Yeah, searching something is also very similar, because I don't want to have an unwanted non-lexical fillers. I can very well, remove those things, right? So if I remove it, it will be even more better. Correction of sentence in chat GPT. That's what. So in chat GPT, like, correction is something like, translation. That's what I say. For example, English to Tamil or English to Hindi. So it's all about, correcting or translating the words. So if your sentence is incorrect, it will translate into a correct word. It's all about one-to-one mapping, word to word or sentence to sentence mapping. So that's how GPT works. So I will give you more insights about this larger language models and how GPT works and all these things very clearly in the upcoming sessions. For now, like, let's stick with the basics. But I know I can get your feeling, because we have a lot more things to cover. But in the coming days, I will slowly enter into neural networks and all the sequential models and other strategies whatsoever. Okay. Thanks for the time. See you again tomorrow. Bye bye.